Okay.
Good.
All right, we're recording.
Good.
So number 4, what all did you find? I can show you my answers if that makes sense. I don't know.
That probably makes sense.
Let's see if I can switch this over. So I think I've got a better camera arrangement now.
It's somewhat
Yeah.
clearer.
Yeah, should be a little better. The first 2 were kind of the same thing. I'm not quite sure why he didn't make some sort of change, but I guess he wrote it a little differently. It was in terms of lambda and v instead of what, k and omega.
What is the conversion between omega and v again?
Well, okay, v, grab a piece of paper.
Because I get the 2 pi over lambda is k, right?
Yeah, essentially, what I like to do is think about it as space and time. And for time, you've got period or frequency or angular frequency. And for space, you would have lambda, the wavelength, k that we've been using, and then there's the other kind of k. This k is the wave vector, or I'd like to call it the wave scalar. Trying to remember what Hecht calls it, the propagation number or something like that, I think.
Mm-hmm.
And then there is the wave number, and he uses a different kind of a k for that. So over here, period is 1 over frequency. Angular frequency is just 2 pi times linear frequency. That gets you back and forth between all the different kinds of time. Over here, lambda is 2 pi over our usual k. And the other k, I've got these written in the wrong order. Let's do them the other way. The usual k we've been using will be down here, and the funny kind of k is up here. So this is what now is usually called a wave number by spectroscopists, and it is just 1 over the wavelength. But the k that we use is an ordinary k, and it's 2 pi over the wavelength. That's all the time conversions. That you probably knew, so I spent all that just telling you what you knew already. Then the thing to remember is that velocity, v, just relates the two.
Okay.
So you can write a velocity as a distance divided by a time. So wavelength divided by period. Or you can write it as omega divided by k, the usual k we've been using. Or there are about 6 other ways of writing this. Those are the 2 that I remember. Distance divided by time and omega divided by k. Omega versus k, you'll often see in physics textbooks. They often will do even graphs of omega versus k, that sort of thing.
Okay.
So that should enable you to transform back and forth from anything to anything else.
John, how can you tell when it's v velocity versus v frequency?
Oh, golly. Yeah. Well, don't call it v frequency. Call it nu frequency. I write a script v for velocity, and nu for frequency is the Greek letter nu, and I write that like this.
Okay.
There is no good answer to this. When you look at these things in books, yeah, oftentimes what they put for a V looks an awful lot like that. You just have to look and see, well, which one is it? It's usually fairly clear from the context which it's being talked about, but it's awfully confusing. You end up with them in a lot of the same formulas, it seems. So you just
Can
have,
you
yeah.
can you quickly say what nu is again?
Nu is frequency. It's just in Hecht, you'll see a lot of the time, he doesn't use F for frequency. He
Oh,
uses
okay.
Greek nu for frequency. And that's pretty common in optics and
Okay.
yeah, in other topics, people don't use F. I don't know why. It's not as if there are a lot of other Fs floating around, at least not in those contexts. So I think it's just dumb. But yeah, I don't make the rules. Just have to live with them. Okay, so back to problem number 4 here. So I just found these two were right in phase. Looking at them, you can see that the, well, he in fact calls that whole thing, the argument of the cosine or sine, he calls that the phase. And they both have the same argument. So they're going to be right in phase. So you're going to get linearly polarized light. It's only a question of what's the axis of polarization. And that's determined entirely by essentially the, what would you say, the vector component, well, the amplitudes, I guess you'd call them, out in front of these things. So if the x component is positive when the y component is negative, then I made a little graph over here and just had a positive x component, negative x, y component. And so the electric field at t equals 0 and z equals 0 is going off that direction. And so it'll oscillate back and forth along that line. And then I find essentially the same for the second one. The only difference being that if you look at t equals 0, you don't learn much because everything is 0. If you look at t equals 0 and z equals 0, you just get 0 for everything. That's a moment when the electric field is 0. So I just picked a different moment in time. I chose when v times t was 1/4, so that I got something, and that gave me a vector going off this direction. It ends up being polarized in exactly the same way. Now, I'm not exactly sure what Hecht means by state the complete polarization. In this case, I said P polarization, and then I gave the axis. I think that's about as much as you can say. I mean, after that, you've got the full formula there. I don't know what exactly we're supposed to do. C gets a little more involved. That one ends up being elliptically polarized. So, and I was just messing around just before. The reason I took a little longer to turn on here is it just occurred to me, oh, well, I guess I could do a little more work and figure out what are the pieces, like how much left and how much right circularly polarized light would go together to make that. Did anybody do that? Nobody tried. Okay. Well, it would be possible. I'll show you in a minute. I don't know. Can you read all that? Is that?
The threes are a little bit hard to make out at times.
Yeah. Okay. Well, anyhow, I went through just the very same kind of analysis that we did before, as an example, and then just made a little graph of these things. And you find out the first one is pointing down with this factor of the square root of 2, and then it's pointing to the right with a factor of the square root of 2. And then it's kind of up and to the left, and then it's more up and not as much to the left, and then up. Anyhow, I just made these little graphs down the line, and then I constructed a diagram of it. Maybe I can draw that one a little bit bigger on a scrap piece of paper here. It was kind of fun. You essentially have only two amplitudes of anything in here. You either get E0 over the square root of 2, or you get E0. So you could make a rather pleasing little diagram here by making a nice little box. So let's call that E0 divided by root 2. And then E0 is going to be square root of 2 larger than that. So make another box just about 40% bigger. And now you can graph all these points very quickly. The first one is right here. It's down. It's got a negative y component, no x component, and the y component is reduced by the square root of 2. And then the second one is right here. It's got an x component reduced by the square root of 2, no y component. The third one has an x component that is the full value. So that's the larger box. And the y value is still reduced by this square root of 2. It's positive. So that puts you right there. And then the fourth one, it just swaps those two. And that ends up right there. And then I did a fifth and a sixth. The fifth one is just a y component going up by the reduced by the square root of 2. And the sixth one is pointing to the left. Anyhow, you can sort of see how it's going and finish the diagram if you want. And I went ahead and numbered them. 1, 2, 3, 4, 5, 6, and 7. And then it's not too hard to connect the dots into a nice ellipse. There you go. That's your elliptical light.
And that is traveling counterclockwise then.
It is, yes, that's going around counterclockwise. And since we are looking at it, if you look back at the original wave, you can see that, well, can you tell which way is it traveling? What direction is it moving? Can
It would
all
come out
figure that
towards us, right?
Well, okay, what are you looking at? How do you tell that?
Does it have to do with the minus pi over 4?
Nope. That's not the issue.
Drew?
Is it whether you have omega or k first?
No,
Okay.
not actually. First of all, note that the k term has only a z component. So it's traveling along the z-axis. The only question is which way. And the direction it's traveling is determined by the relative signs of the time and k parts. When those are opposite in sign, it's traveling in the positive z direction. If they have the same sign, then it's traveling in the negative z direction. That's how you tell. So this is traveling in the positive z direction because the omega t and kz have opposite signs. I'm trying to think, I think, Aaron, you were wondering whether the minus pi over 4, that would have to do I think with which way around it goes. I think that would determine the direction of
Okay.
rotation, not the direction of travel.
Okay.
Um,
So is a positive z direction left hand the same as a negative z direction right hand?
I don't know for sure. In other words, if you just flip the sign, what would you have here? I think you're right. If you were to change the sign on the K term, the KZ term, I think then it would be rotating, it would be the opposite rotation sense in that case.
Okay.
I think that's right. It's a tricky thing. You have to remember the fact that when you take a screw and flip it end for end, if it's a right-handed screw and you flip it over, it's still a right-handed screw. You can't change a right-handed screw by just, but here you're doing it in the math. And I think, yeah, in fact, that's true. By changing the sign on the K term, that's essentially the same as reflecting the z-axis. You're changing the sign on the z-axis, if you like.
Okay.
And that will have to change the sense of it. That's like a reflection. And a reflection always changes the handedness of things. So I think that's right.
And what does changing the sign between the I hat and the J hat terms do?
Yeah, those out there, that will determine, I believe, the orientation of this whole thing. Which way
Okay.
the major axis and the minor axis,
Okay.
determined by that stuff. Okay, well, I don't want to spend all of our time on this. I did have a little fun.
Question.
Pardon?
I have a question. So
Sure.
do we need to do the analysis every time to solve? Because when I solved it, I didn't actually do any of the graphs. I just looked at the equation.
You just looked at it
all
and
of
said,
them to
oh,
cosine.
pi over 4, yeah, that's got to
Yeah,
be elliptical. Sure.
elliptical.
No, that's fine. If you know that. I want to do all this so that you can see how to get through it
Mhm.
if you aren't quite sure. But once you do know what's going on, there's no need that you have to do all of this. It's a lot of tedium. Although it's kind of fun too. I don't know. Decide what you think is fun.
And then I have a real quick question on that too.
Yeah.
So Heck like to change everything to cosine, but there's no real benefit to that, right?
I don't see one. I don't see any, no.
Yeah, okay.
You certainly could, but I mean, I suppose if you were considering putting it into complex form, then you would need to.
Okay.
But if you're not going to do that, I don't see what the benefit would be.
Yeah.
I think it makes it quicker because if everything in cosine, you can see that we have pi over 2, so it must be e square root of e over the square root of 2, and
Yeah,
it's alternating.
It's a matter of taste. It's sort of what you're accustomed to looking at, and if you've been looking at cosines forever and ever, you might as well just stick everything in cosines. But yeah, whichever. Okay, here I just got to show you a little bit of what I was doing. Interested to note that he does talk about the fact that elliptically polarized light can be considered the sum of right and left circularly polarized light, but not with the same magnitude. In other words, you'd have, in this case, what did we say? This is left polarized light because it's going around counterclockwise as we look at it and it's coming toward us. That was the thing we didn't quite finish before. So because we figured out that this thing is traveling in the positive z direction, well, the positive z axis is pointing straight at us. And so it's coming straight at us. And when it turns counterclockwise as we look at it coming toward us, then it's left polarized. But this isn't circularly polarized, it's elliptical. And so you could consider that a mixture of left and right, presumably in this case with a stronger left component and a weaker right component. To figure out what those two are, I think what you have to do is find the major and minor axes. Figure out what is the electric field in the strongest direction here, and then what is it in the weakest direction perpendicular to that. And then you have to work out what two vectors add up to those, and when they subtract, you get the difference that's the smaller one, and that gives you your right and left circularly polarized terms. But I haven't done the math for that. I just found the magnitudes of those two. Okay, let's move on. Let's move on to D. Hey, maybe this will help. Is that better or worse?
It's
About
better.
the same,
About the same.
just brighter.
Just brighter. Okay. Well, I'm still trying to figure out lighting. I haven't got that worked out better. But I do now have an upgraded account, so we can go for more than 40 minutes if we need to here. So here is part D, and I went through all the details again, and up to hell, you probably just looked at it and said, oh, that's pi over 2, and so they're shifted by exactly 90 degrees. This is circularly polarized. You have to think a little bit to figure out which way it's going around, maybe.
The sign of bi.
Yeah, okay, so,
Sorry.
right, if you can think through it, then good for you. So I just made myself a little graph here again, and found it going around. This time it's going around clockwise. So this is right polarized, according to these definitions. And it's perfectly circular polarization because they're shifted by exactly pi over 2. So the magnitude of the electric field is constant as it rotates around. Any questions? All right, let's move on to number 8. Oh, this one I haven't looked at for a little while. So you're supposed to write the equation for this P state, linear polarization along a K vector that is in the XY plane, but it's at 45 degrees to the x-axis. It took me a little while to figure out what he's describing here, but I finally decided this is light that's moving off in the, 45 degrees to X and to Y. And then the polarization is in this plane perpendicular to that direction of propagation. Is that what you all were trying to achieve? No.
No.
Not at all.
Not at all.
Yeah.
We were reading it as similar to 4A, but 90 degrees from that.
Yeah.
4A. Ah, so you had it traveling along the Z direction.
Correct.
Yeah, no, I don't think that's right.
No, it's supposed to be traveling in the XY direction.
Yeah,
Okay.
so it's propagating along a line in the XY plane. That can't be the Z axis. So its propagation direction is in the XY plane.
Mhm.
And it's at 45 degrees to the x-axis.
There's something you have next to when you wrote the expression for k. It's like square root of 2 times something. What is this something?
Yeah, what I'm doing there is just
In the
writing
magnitude?
this. This is a unit vector, essentially. So I just constructed a unit vector that's along
X and Y. Yeah.
equally along x and y. It's 45 degrees to x. What I'm seeing is there's a kind of an ambiguity. He says it's 45 degrees to the x-axis, but that doesn't have to mean between the x and y-axis. It could mean between the x and negative y-axis. He doesn't exactly exclude that.
Mhm.
But let's not worry about that.
Mhm.
So I just assumed that it's propagating along this sort of xy direction. And I constructed a unit vector along that direction and then multiplied it by just k, which is the number k, not the vector. I let the unit vector give it a direction, and then it has this magnitude of whatever k is. K would be omega divided by c. I think we're given, what are we given? Nothing. Oh no, we are given omega. It's just omega. He doesn't give a number for it, but we're supposed to do it in terms of omega. So you could say k is omega divided by c. Maybe I need to write this bigger. Am I too small here for you guys to?
I thought it was E for.
Yeah, okay. Let me redo this all quite a bit larger. All right. So first off, I'm assuming that this beam is propagating along this direction. And its polarization is sort of in this plane, back and forth, like so. Does that make sense to you all? That's what I'm trying to describe mathematically. So the first thing is to get a k vector. So I need a k vector, and I decided to say my k vector is going to be the magnitude of k times 1 over root 2 I hat plus 1 over root 2 j hat. So this is my sort of unit vector pointing in the direction this is propagating, and then I'm multiplying it by the magnitude of k. Does that make sense? And then further, since k is not what we're given omega, and this is supposed to be light, so we can use one of those equations I was just showing to all of you. V, we'll call it C this time, is omega divided by k. So solving that, k is omega divided by c. So from that, my k vector could now be written as omega divided by c times 1 over root 2 I hat plus 1 over root 2 j hat. That would be my k vector. So what I'm going to do is write this as, well, normally you write a wave as some E0 sine or cosine. Should we do it in cosine? What does he say? Nope, should be a sine. If you look at how it starts, we want to use sines this time. Sine of I think I'll write it as omega t minus k kx, but x isn't the right thing to put here. What you really want is k vector dot r vector. That's the more generic form of a wave. If you remember way back in the earlier chapters, that's how you describe a wave that's traveling in 3 dimensions. So we've just found the k vector over here. So now I can write this as some E0, this is also a vector, times the sine of omega t minus, and now I would write this whole thing out as omega divided by c, I over root 2 plus j over root 2, and then dot that with the r vector, which would be x I hat plus y j hat. This is just the r vector. The r vector is just our coordinate vector. It's a vector that takes you to whatever your x and y coordinates are. If you're trying to find the electric field at a particular point, this is the vector that takes you to that point. So going ahead and writing out what that dot product turns into is we lose all the i's and the j's. We would have omega t minus, oh, what are we going to have here? Omega x over root 2c. And then another term that's going to be omega y divided by root 2c.
Is that a minus or a plus in there?
Well, a minus, these are added. The minus sign out here applies to all of those terms.
Okay.
That would be one way to write it. There would be several other ways. You could factor an omega out of everything here if you wanted to. Not sure how you want to write it at this point. The other thing we have to do is get an expression for this E0 out here, the vector expression for that. And we want this to be linearly polarized, and it's going to have x and y components. So they're going to be, in a sense, they're just going to be E0 over root 2 I hat, and then out here an E0 over root 2 j hat. The only question is the signs, if you know what I mean. Which ones are positive, which ones are negative. They've got to be in phase for this to be linearly polarized. And if you think about it, to make something that heads off this direction, you know, I lost my paper here. I want it to be going in back and forth. You have to have opposite signs, is what you're going to end up with. So I would make the x plus and the y negative. I don't think it would matter. You could do it either way. So this would multiply the sine of omega t minus omega over root 2c times x plus y, I guess. And then over here would be the sine of omega t minus omega over root 2c times x plus y. Something like that would be a reasonable answer to this question. This is a hard problem, a very hard problem. I'm glad I decided not to give you a quiz like this one. I was actually debating that at one point, but thought better of it. You don't think you're ready for that one, Ben? All right. Well, so you all ended up with something very different than this. If you're thinking more like problem 4, I will have to keep my notes on this. This was 8, 8. I've got other notes there. Let's move on.
Cosine, but I had like a shift of negative pi
Oh, did you?
in one of the directions.
Okay. All right. How about 12? That should have been a little bit easier, I'm hoping. Am I right?
Yes.
We get through 12?
It's just applying Mauler's law, right?
Malice's law.
Malice's law.
Yeah, I'm not sure how you're supposed to say it, but yeah. So I got 0.25. All right, that was straightforward enough. Shall we look then at 28 instead?
Mm-hmm.
So how did you find that one? This took a little bit more thought.
It's also Malice's law, right?
It is. The only tricky part is what do you do with that very first polarizer? When you
Cuts it
start-
in half.
Divided by half.
It divides it in half. Yes, there you go. If you know that, then it's pretty straightforward. So I just went through the whole thing and got, see if I can get them all on here. There we go. So the first polarizer cuts it down by 50%, so that's 0.5 here. And then after that, each one is at 30 degrees, and that cuts it down exactly 3/4, or 75%. So just multiplying 3 of those together and the 50% at the beginning, I got 21%, or 42.2 watts per square meter. We all got that?
Yep.
Great. Well, Aaron is lost, but here he comes. Okay. Now, just for the fun of it, I mean, I don't know if you can see what's going on here. You've got randomly polarized, and then you make it linearly polarized, and then go through a series of these things to rotate the plane of polarization from vertical to horizontal. What would happen if you did the same thing, but with fewer polarizers? So they went through 3 steps, each of them 30 degrees. What if you went through 2 steps, each of them 45 degrees? What would happen? Well, that's what I've calculated down here. At 45 degrees, that's 1 over the square root of 2 squared is 0.5, according to Malice's law. So in that case, you'd have the initial 0.5 that you always have, and then 2 more 0.5 for 0.125 or 0.8, I guess. And so
I don't know if the shelter
ultimate
talks, but
result-
they're asking people not to go out.
Oh, we're hearing somebody's background noise here.
That might,
Okay. So the ultimate result would be 25 watts per square meter. And the point of all this is just to show that that's less than the 42. So going through several small steps gives you a larger final intensity than if you try to take it in a few big
My
steps.
cats?
Of
No, we're taking
course, the
maybe a kitten to start with.
ultimate end of that would be
But
if you were to just do it in one step, all of it in one step, you'd be going 90 degrees in one step.
Did you adopt Marla from a shelter?
In
Not
that.
here.
Marla is,
Yeah.
and it's visible in her demeanor. Marla's a farm cat.
Okay.
From Old Order Mennonite farm up in, near Yellow Creek.
All right.
And
Everybody understand that one?
litter of 3. And they thought she was a girl. It
Right.
turned out not to be.
All right.
Right.
I think your mic's on again.
So she came.
We're hearing. There we go.
Sorry, I was trying to keep it muted and it must have messed up.
Yeah, well, I messed up in the other direction. I spent a couple of hours recording a bunch of clips for general physics and discovered that my mic was muted. It's got a little touch switch on it. I was so disgusted. I just gave up and went to bed.
Well, there's a physics video about this. Like how physics professor who keeps the thing muted and keep talking. Nobody hears it. I'll send you the video.
I did exactly that. The very first one, I went through the whole process and had a perfectly good video, and it was fine. Somewhere along the line, I touched it. It's one of these that's got a little touch thing on it. All you have to do is touch it with your finger, and it switches. And there's just a slight blue light. It's not very noticeable to tell you that it's on. And I didn't notice that wasn't on. So now I'm trying to be more careful and check it. I'd be tempted to just buy a new microphone, but haven't done so yet. All right, let's move on. We've got more fun to be had here. I think we already talked about this 56, didn't we? The business of a isn't that where you're supposed to identify which one is which? Yeah, linear polarizer and a quarter wave plate. We've already talked about that. That the quarter wave plate looks clear, and the polarizer looks kind of darkish, so you can very easily tell the difference between the two. Okay, now we've got to go on to this last one. This is going to be great fun. So if you looked at 68, you should have seen this is again a description of these this combination of a quarter wave plate and a polarizer that creates circularly polarized light. I'm curious what you all came up with. What did you decide? Did you answer it somehow?
I think we decided that it would not let any light back through.
Okay, and say more. Why?
Sure.
So, you want to go, Ben?
No, go ahead, Aaron.
So the light that comes in gets taken from going in all directions to being circularly polarized
Yeah.
and let through because it's shifted by a quarter of a wavelength. And then as it bounces back, it gets shifted another quarter, so it is 90 degrees from how it was originally and gets blocked by the polarizer.
It doesn't change when it gets bounced back, does it? It's just that we're looking at it different, so it goes in a different
Going
direction.
from right hand to left hand circularized, I think.
These are all the right questions. You've got the right pieces are in the conversation. We've got to connect them together the right way. I did some thinking about this, and then I finally did an actual experiment, which I'll show you here in a minute. But so you know that when it goes through, let's assume this thing is creating, yeah, it says that this is creating a right circularly polarized light that comes through. The first thing you might ask is, what if you had a source of right circularly polarized light? Could you shine it back through that thing? Another way of putting it is to say this thing creates right circularly polarized light. Is it also an analyzer, a detector, a filter admitting right circularly polarized light?
I don't think so.
Would it, so first the polarizer would make it linear and cut out half of the right circularly polarized light. So it would let it through, but only at half the intensity?
Well, remember, if we're coming through from the other direction. So the first thing it's going to encounter is the quarter wave plate.
Oh, coming back the other way.
Coming
Okay.
back through. So I'm imagining, we're replacing the screen now and just saying we've got a source that's shining, but from that direction.
Okay.
So it's trying to shine back through. Would this be an analyzer? If you try to shine through the regular direction, if you've got right circularly polarized light, doesn't matter. A polarizer will give you, oh, what do you get? I don't think it matters. Either one would come through in the straight through direction. You could feed in either polarization, either right or left, would pass through and become only right circularly polarized. But
At the same intensity?
I think so. I think they'd both be reduced because you would both get turned into linear polarized light with no memory of which way it was rotating.
Okay.
And then the quarter wave plate would turn it into circularly polarized light. So they would both be reduced, yeah.
Okay.
But coming through from the back, that's the question. What happens when you come through from the back? And I've decided that, in fact, it generates right circularly polarized light. It also admits right circularly polarized light. And the reason for that is if you draw your diagram with this wave going on through and have it, if you made a diagram with the electric field vector rotating like a screw, then it creates this right-handed screw. As it propagates forward, it's making this right-handed screw. Now flip that screw around, it's still a right-handed screw, but now it's coming back through and the diagram would look exactly the same. You wouldn't know which direction the light is going. So this serves as both a creator and a filter or analyzer for right circularly polarized light. So works both ways. Now, what about the screen? So will this be bright or dark? You guys decided it was dark, but for a mixed up bunch of reasons here that weren't quite clear. I want to see if we can be a little more clear. What is the crucial factor here that you need to think about?
Does it have to do with it going through a polarizer twice?
Nope. It's all about the screen.
It's all about the screen.
Yeah. It plays a crucial role here. Let me give you a hint.
The screen is emitting light. Is that correct?
No, it's reflecting it.
So it is not backlit.
No.
Okay.
Well, it might be.
Reflecting.
It's reflecting. The whole purpose of this, at least he hints at it, is that you're trying to get rid of the reflection of room light that comes off your screen. You want to be able to see the light that comes from the screen, but not see the light that's reflected off of it. And if I may do a demonstration here, here, this would seem to be the obvious thing to show you. If I can position all this stuff correctly. So what's odd about the reflected version of this?
That it's a mirror image.
Yeah, it's a mirror image. Or here would be another possibility. Which hand am I holding up?
Well, it must be your left hand because it's got your wedding ring on it.
Yeah. Anyhow, the point of all this is to remind you of one of the properties of mirror reflections is that they change right hand into left hand, and they do the same for circularly polarized light. If you want a more of a mathematical proof of that, you can just say, well, you're switching one of the axes. You're changing the sign on one of the axes. Pick the z-axis if it's traveling along the z-axis. Now you've switched the sign on the z-axis. So it's propagating the other way, but everything else is still the same. And so if you're going to think about which direction, which kind of polarization it is, you have to say, well, which way are you looking? And now you're looking the other way at it. Anyhow, it reverses the direction of the polarization. Well, now I have to show you this cute little demonstration. So I'll switch cameras here. Okay. Now, if I lay this down, you're seeing right here, this is the camera, and that other globe up there is just the light on the ceiling that's not on right now. So here is one of these pairs of glasses, and do you see how they are dark? I need more light here. Maybe I'll lighten up the ceiling. Is that better? There we go. Now you can see it better. See how dark they are. But now watch this.
So it's only blocking out the reflected light, not the light that's originating behind the polarizer or behind
Exactly.
this device.
But are you also noticing that it blocks the reflected light that's going through the very same lens? But if it goes through the other one, it doesn't block it.
Oh.
That's what I wanted you to notice. See, one lens is dark and the other one appears light. Is that cool? And you can do this. This is the best way I can show it to you here. But if you have a pair of these glasses, all you have to do is walk to a bathroom and look at yourself in the mirror while you're wearing them. And each eye will see that eye as dark, and the other eye, it will see it. It will seem clear. So right now, it's as if we're looking through the left eye. And we're seeing, in the mirror, we're seeing ourselves. And that eye on the same, I don't want to call it the left eye, but that eye that's on the same side of your head or whatever, is dark. And the other one, the crossed one, if you like, is clear. And now if we look with our other eye, itself looks dark, but the other one looks clear. So anyhow, I thought that was cool when I discovered it. And it's just exactly what they're talking about in this problem. So I guess you could lay this stuff on your computer screen and greatly reduce reflected light in principle. I don't know that anybody does this. It's probably kind of expensive to use that much across your whole screen, but it could be done. Is that cool or what?
It's really cool, John.
I was so happy when I discovered that. Oh. So the next time you go and see a 3D movie, pilfer the glasses like I always do, and then have some fun with it. All right, I think we're done for now. And there is a quiz that is going to come online at 3 o'clock here just in a couple of minutes. And all you do is take out a sheet of paper, work out your stuff, and then snap a picture of it and submit it as your answer. I think I gave you, I don't remember how much time I gave you, 2 or 3 hours. It's not going to take most of you more than, all of you really, more than about, I don't know, 15 or 20 minutes probably to get it done. So it shouldn't be difficult. It's not one of the more difficult problems. But that's all right. We'll rectify that next week. Next week when we get into interference, I'll give you something a little bit more to chew on during a quiz. But don't worry. It's not that I'm trying to pound you. What I want to do is get into stuff that is a little bit more mathematically involved, but that you can actually do. That's what we all enjoy, is finding those problems that you can work out, but that do take a little bit of work to get through. This chapter seemed to have, well, I don't know. Anyhow, we'll see how that goes. That's what I'm trying for. Boy, how about the color of my hand? Isn't that beautiful purple there on my screen? Golly, what have I got? Coronavirus, I don't know. Have to work on the white balance here. All right, so I think we'll meet again at 2 tomorrow, and we'll start on that new material and start charging away. In the meantime, you can look at that quiz and see if you can get that done this afternoon. It's open for several hours. I don't remember how long. Just watch out that those times are all Eastern times in Moodle. It doesn't convert if you're in a different time zone. You've probably figured that out by now.
John, are you gonna upload this video on Moodle?
This one, I sure can. Yep,
Okay.
I've already put the other ones up. They're up there now. So I'll add this one to the group. Okay, that's it. Have a good day. See you tomorrow.